Welcome to The Explainer. Today we are tackling a genuinely baffling paradox in the world of artificial intelligence. If you look at the cutting-edge AI research coming out of academia right now, it is packed with incredibly sophisticated, constantly evolving memory architectures. Yet, if you look under the hood of billion-dollar enterprises, we're talking regulated spaces like mortgage underwriting or clinical review, they deliberately use what looks like a much weaker, simpler form of AI memory. So why on earth would a massive bank or hospital intentionally handicap its own AI? Well, that is the enterprise AI paradox, and today we're going to solve it. All right, let's just breeze through today's roadmap. We're covering the enterprise AI paradox, the 4 rules of regulated AI, the flaw in stateful memory, our stateless solution known as DPM, performance, cost, and scale, and finally, exactly when to use DPM. Section 1. The enterprise AI paradox. Why simple beats complex in the real world. So I really want to pose this question directly to you. Why would an enterprise purposefully use weaker AI memory? Academic memory architectures have completely exploded over the last decade. You've got typed routing, hierarchical consolidation, belief state tracking, the whole shebang. But when an enterprise actually deploys an AI agent to, say, adjudicate a complex insurance claim, they throw all of that out the window. The divide here is honestly pretty stark. Academics love complex, stateful systems that are constantly evolving and updating their internal representations. But enterprises, they overwhelmingly rely on really simple, arguably weaker stateless setups, specifically retrieval-augmented generation, or RAG. And it turns out this isn't because enterprises are just behind the times. Not at all. It's because they are operating under an entirely different set of hidden constraints. Which brings us to Section 2, the 4 rules of regulated AI, the load-bearing pillars of the enterprise. Okay, so these are the 4 non-negotiable pillars. First up, deterministic replay. Look, if a denied loan applicant asks why they were rejected 6 months later, you must be able to replay that exact decision perfectly. Second, auditable rationale. You need a concrete, traceable reason for every single decision, not some random AI hallucination. Third, multi-tenant isolation. This is absolutely crucial. One applicant's documents literally cannot leak into the memory space of another. And fourth, horizontal scale. The system has to process thousands of concurrent decisions without bottlenecking. Now, when we stack different memory architectures against those 4 rules, the winner becomes incredibly obvious. DPM, which stands for Deterministic Projection Memory, satisfies all 4 of those enterprise properties natively. It's just green across the board. But stateful architectures, they fail on almost every single count. To make them actually work in an enterprise setting, you have to engineer these massive, messy retrofits just to keep them compliant. Section 3. The flaw in stateful memory, the AI game of telephone. Let's clearly define what the problem is here. Stateful memory is an architecture that incrementally updates and summarizes its internal memory as it goes along. The absolute key word here is updates. The memory the AI has at the moment of decision is entirely dependent on the specific path of all its previous memory updates. Think of it like this step-by-step flow. An event occurs, the AI summarizes it. A new event occurs, and the AI summarizes the summary. It's literally a game of telephone. Every single time the AI summarizes its memory, it has to compress information. And when that happens, a little piece of the raw truth is lost, or altered, or reframed. So if an auditor comes knocking and asks to trace a specific decision back to a specific document, you can't easily do it. The original fact has been summarized a dozen times over, and your auditable rationale is just, poof, destroyed. Section 4. The stateless solution, DPM. Let's look at the accountant's ledger approach. So meet the hero of our explainer, DPM, or Deterministic Projection Memory. This is a beautifully elegant, stateless solution that finally bridges that massive gap between the high performance of advanced AI and the incredibly strict compliance demands of the real-world enterprise. Here's how this incredibly simple yet powerful process actually works. Step 1. You maintain an immutable append-only event log. You never erase, you never summarize, and you never rewrite history. It's exactly like an accountant recording transactions in a ledger. Step 2. At decision time, you perform a single projection. You just hand the AI the totally unaltered log and ask it to make a decision, once. And the crucial difference here is what we call the 1 versus n asymmetry. Think about it. Auditing a stateful system requires investigating every single summary it ever made. That's often 80 or more AI calls, which is a total auditing nightmare. DPM reduces that entire mess to exactly one AI call at the very end. It's a single, perfectly reconstructible projection pulled straight from the raw data. Section 5. Performance, cost, and scale. Because, the proof is always in the data. The researchers evaluated these architectures under several different memory constraints. And the really magic number here is 20x. When these systems were forced to operate under a very tight memory budget, specifically a 20x compression ratio, something absolutely fascinating happened. When put to the test under those tight memory budgets, DPM completely dominates the stateful baseline. I mean, it pulls ahead by over half a point in both factual precision and reasoning coherence. In statistical terms, that's a Cohen's H over 1.1, which is a massive effect size. It means the difference in reliability isn't just noticeable, it is practically night and day. When the AI is forced to compress data heavily, that stateful telephone game just falls apart. But DPM, it stays rock solid. And that advantage becomes even more obvious as data compression increases. As you force the system to compress more data, heading right toward that 20x mark, DPM's lead just spikes. Because incremental summarization is lossy, right? Errors compound over dozens of events. DPM completely dodges those compounding errors by simply waiting until the very end to consolidate everything. But wait, it is not just about being more accurate. It's about pure efficiency. DPM is up to 15x faster than stateful memory. And the cost? Get this, DPM costs just 1.4 cents per run compared to 16.5 cents for the baseline. So you're getting better compliance, way better accuracy at tight budgets, an order of magnitude more speed, and you're doing it all for a fraction of the cost. It's a no-brainer. Section 6. When to use DPM, the TAMS heuristic. To make all of this actionable, the researchers developed a really straightforward framework called TAMS, which stands for Task Adaptive Memory Selection. Think of this as your ultimate takeaway toolkit if you're a software engineer or an AI architect looking to build real-world systems today. The framework is crystal clear. If your deployment requires an audit-ready rationale, deterministic replay, or multi-tenant isolation, which, let's be honest, almost all enterprise apps do, you use DPM. If you need a compression ratio greater than 10x, you use DPM. It is the mandatory load-bearing choice here. Only if you meet literally none of those conditions can you start choosing a stateful architecture just based on preference. Which brings us to our final thought. I want you to look at the AI systems your own organization is building or using right now. Ask yourself, could your current AI stack actually survive a strict regulatory audit today? If it's constantly summarizing, mutating, and overwriting its own history, well, the answer might be no. By shifting to a stateless log and project architecture like DPM, you don't just protect yourself from the auditors, you're actually building a faster, cheaper, and far more precise AI. Thanks so much for joining me on this explainer, and I will see you next time.